tonight is my great pleasure and honor to introduce Daniela Kröhnert and Lukas Allner from the University of Applied Arts in Vienna, die Angewandte. And they're going to be talking about their research project, which has actually been published already like 5 or 6 years ago, I think, in the book. Or is it that long ago? Oh, 2 years ago? Okay, yeah. But it's a really fantastic project, Conceptual Joining, where they worked with tree forks as structural systems, so very, very close to the brief that we've been working on with the students. Most of you are students in this term. Yeah, I'm going to leave the stage to you. It's great to have you here, yeah, there you go.
Yeah, then first of all, thanks for the invitation. And it's also a premiere for us. It's the first time we're presenting physically. So we've shown the work a couple of times via Zoom. It's the first time we're doing it physical.
Yeah.
It's also cool.
And we're also having a workshop tomorrow and the day after, which we're also very much looking forward to. So as an introduction to our work, or the workshop also, we have this presentation.
I mean, just a quick note about us. We both also studied architecture, worked a bit in architecture, and then found our way, smart, timer, back to academia. For different reasons. And in 2016 we wrote the first research application, and in Austria they have an arts-based research funding program from the FWF, it's the Austrian Science Fund, which is quite beautiful because you can go in with quite open questions and be more explorative. It doesn't need to have like A to Z, like a normal or standard classical research fund in, for example, the medical science. And this project ran for 4 years, and it was 4 researchers, so mainly Lukas and I, and then there was also Philipp Reinsberg and Mechthild Weber, and the lead was Christoph Kaltenbrunner, so he's the professor at the Angewandte who was kind of the lead in the project, but the main work was done by us.
We literally came to him with the proposal, asked him whether he would submit it for us, pretty much.
Because as it is always in academia, you need...
We have to cut this from the video in case he watches.
No. He always introduces it like that. No, because it's also a little bit quite like a critique into academia sometimes, because it's hard to get research funding if you're not accomplished.
But also a great opportunity for us to start in completely naive and not knowing what research really is. Having the opportunity also that Christoph offered us to support us in this sort of quest. And in the end, of course, he also contributed quite a lot. So, let's go.
Yeah, and so we got 350,000 to basically play around for 4 years and follow our own interests. And we went in with 3 basic questions or things we wanted to look at. And on this, I move a bit.
It's okay.
Yeah. And so one of the big interests was when you look back in history, you see on the left side the old Walton Bridge, designed by William Etheridge. And he was a carpenter, and he went quite intuitive at that time in building a bridge following the force flow in the bridge. And then during industrialization, that more intuitive, complex approach gave way to standardization and repetition, basically, in favor of increasing economy, And so we were wondering if we could like with modern technologies, like go back to this more intuitive approach in building structures.
But without losing the mathematical and engineering approach that industrialization also brought about. Comparing to the former example, the crafts-based sort of bridge, the intuitive approach in that time didn't have the possibility of calculating, so they were more basing their sort of designs on experience, so on guess and more guessing or educated guesses rather than precise calculations. So
the heuristic approach.
Here with the help of computers, that was the hypothesis of this project, was can we do both?
Yeah, and especially as we like focused our research on wood, also looking at the anisotropy, for example, like the fiber structure, so this material-based approach of a material that's not homogeneous and has its own way of what it wants to be. And also with modern technologies, we can actually really look into the wood and analyze a lot of its physicalities and structural properties.
Yeah, and if you look at it, if you look at wood in this way, you realize that wood doesn't work well with standardization to begin with. So we were questioning the sort of if this could be also an opportunity.
Yeah, and then even further, and we are quite influenced by that because we've been living in Vienna for a long time, is looking at new technological invention and how they can inspire a complete new aesthetics. Like in this example, the tonnet furniture, where they developed the bentwood technique, and then a whole new language of design came about. And this, again, very much connected to technological inventions. And this, again, counts for us because we were interested, or like our focus is, everything we do is infused by the modern digital technologies and digital fabrication. So that's kind of the new approach. And with this, we looked at mainly 2 projects over the course of the years. And one was starting at like the traditional craftsperson or craftsman joint, and how that can be pushed to a new level with digital technologies. And the other is looking at actually naturally grown wood and its structure, where we take it as it comes from the forest.
So just to give you a brief overlook, we are showing you briefly this project, which we haven't talked a lot about, but we figured it would still be interesting to see. Obviously, it's not about grown forms of wood or the forked branches, but more about joinery. But so I'm going to go through this, or we show this briefly and then switch to the other project, one after the other. Okay, so here we started off with the premise of traditional joinery in the contemporary digital context. And one of the key examples we also looked at physically, we were there, was this project by Kengo Kuma and Jun Sato in Tokyo. And what's astonishing about it is that this building is constructed by this incredible amount of tiny sticks, which is the primary structure. But it's not only the structure, but it also acts architecturally like a filter. It's not clear where the boundary of the building really is. I mean, of course, at some point there's an envelope and there's a glazing, but spatially it's quite fuzzy. And it's based on the principle of interlocking sticks. So we invited this engineer who is interestingly working very conceptually. Also, we invited him to Vienna to do a workshop with us, with students. So based on that sort of idea of interlocking sticks without using glue or connectors, which sort of forms or structural systems can be composed based on the joining principle, so a bottom-up sort of approach. And then on the right-hand side you see the example after 2 or 3 days or so, something like that, which was kind of a sculpture but also a structure, and that we took on, or we took it further into. Okay, here's some slides. Anyways, we refined the design and the computer optimized it, systematized the approach, and then in the end, this is what you saw in the videos there. We're able to fabricate all the members, all the pieces with a CNC truss cutting machine at the vocational school for carpenters in Austria. In another part of Austria, and then we had this sort of kit of parts that you see at the bottom right. Oops. Oh, there you go. And with this kit of part, you could pretty much assemble the structure by interlocking these sticks, and roughly the concept worked like in a stacking system. So you would build up sticks that would interlock, and oftentimes a third member would lock the sort of connection. And then the argument was that the simplicity of the joint, being a half-lap interlocking joint, very simple, is only possible to stabilize a structure with a spatially complex organization. So the overall complexity works together with the simplicity and the detail. And in the end, of course, every single member is different. It's all unique parts. It's a kind of a puzzle. But we already realized, okay, there are systematic sort of moments in it, which we brought along into the next step, systematizing this sort of unique sculpture into a modular system. And for this, we used a case study as a table. So we were thinking about, okay, how could we use this sort of interlocking system as a table construction? And here you see 3 instances of this development. No, actually only 2. So at the top you see the first sort of quick test, and then that was okay working. And then the second, that's the row below. Is perhaps the more interesting one, because it really literally works only with gravity. So what you do first is you assemble 2 of these sort of star-like structures. They are identical, so rotated 100 degrees. That's what this diagram is trying to illustrate. So you have twice this sort of module, and then 2 horizontal members. Connect the 2 they don't have any details, they just lock in, and then the tabletop has these CNC cutouts, and it fixates the tips of the sticks to stabilize the whole table. So you can't really carry it around, but you can assemble and disassemble it quickly.
Yeah, so this is in general like a dry construction. You can disassemble it as quickly as you can reassemble it and move it to different moments. And I think this is also something we probably should have added in the beginning, is that one main focus of the project was also to not use metal fasteners, because in the industrialization process of wood, wood only became a filling material. So it's cut up and then re-glued back together. So to get rid of this fibrous structure and its own will, what it wants to do. And so we were trying to just work with wood and wood joinery.
So continuing from the moment of this sort of table study, we were trying to push this idea back into an architectural scale, and not only did we systematize this sort of structure of interlocking timber, like linear elements, we also brought along these sort of panels that would interconnect with the structure to for once also stabilize it or introduce bracing, but also indicate some sort of moments of envelope or something that could become a building or something like that. and also the idea here was that it could be expanded theoretically infinitely, and you see here in this image that many of the joints were not used, so indicating that you could keep building it or continuing it, or even disassembling it over here and assembling it on the other side, and whilst doing so also modify the configuration. So this was the set of parts. Theoretically this would be all the types that exist in this structure, but in reality since we had to cut them on the floor, there were special types as well, so it was a sort of compromise. And this is another aspect. We used AR, really like smartphone, tool to assemble the structure or put the puzzle together, pretty much. So we didn't have any drawings, but at that time it was a very basic process, but very effective.
But also necessary because of the way it works, that you always add the last beam to fix the joint in place. There's an order of members on how you assemble the structure and disassemble, and that is not something that's easily drawn in a plan. Otherwise you end up with a
How many different types of how many stick types were there? Like, you have one that always ends the same way, or is it like a set of 10?
10.
These are the types that exist, and they have been grouped into modules. So these 4 would build a mod. So this is one of the modules, I think, or it's even a combined module. So there was a sort of rule to how things would come together, but then with the app we would have labels, and the labels were also printed on the sticks, because this robotic machine, the truss cutting machine, can route, cut, and change tools, but it also can use a pen and write on the piece. So it would write the labels on it, which is funny. It's quite astonishing, the sort of robotic aggregate in this thing. And this was by the way, this is the minimum profile width dimension that we could use. And the carpenters were laughing at us. They were saying, this is like a toy scale. This is not real. For them it's like minimum, like 10 by 10 or so.
Yeah, these machines are standard in the industry for cutting wood beams.
And usually for structures that are usually hidden, right, underneath in roofs, and this amazing technology is used in the sort of invisible space. So we were hoping that this could also, this could be used for architecture, or like space that you could experience.
Yeah, and in contrast to this more technical approach where we designed the joint and the system, in the other project we thought we look at the naturally occurring joint in a tree. So in hardwood, this is actually, if you use the joint as nature designed it, according to the force flows, it's stronger than anything you can connect manually or technologically. This is why in wood construction you have a wood beam connected to another one with like these steel plates with 20 screws in it, because the forces want to flow in cross section and not in points, and so this is why you need a lot of screws. And so in this one we look back at, for example, here on the left side, that's the ship construction manual from the 1700s. Yeah, so it's
18th century.
Yeah, 18th century, so 1700s, where the shipbuilders actually went into the forest and looked for trees that were grown in a curve that fit the shape of the hull of the ship to build it like that. And this is still done traditionally to a certain way in India, for example. That's the image on the right side. And they also use this heavily in tool manufacturing. Like if they needed a grass cutting tool, they went and looked for something that grew in that shape. You might have heard something about that last week from Michael Grabner, because we consulted with him also when we started the project. And so this was this approach. We look at the natural joint, and then we had some sketches, ideas, and how to work with it. And we wanted to take what's in traditional wood construction. The knot is usually the weak point, and all the industry tries to cut wood as orthogonal to the knots as possible, and try to get boards with no knots. And so quite quickly we embraced that and say we work with the knot. And then instead of designing a complex joint, how to use the existing one. And our project is situated in between these two approaches. On the left side, that's a living bridge. Quite interesting, traditional construction method that they grow bridges over lifespan of a person, basically. And if you're interested in that, Ferdinand Ludwig from Munich, from the TU Munich at the Baubotanik Institute, he's heavily researching that and also developing methods now to do that. But we were interested in the now and not waiting for a long time. And on the right side, that's one of the first examples from architecture. Is the wood chip barn. They built that in Hook Park at the AA in Great Britain. And what you see here is that they simply used the wood beams and built a traditional scaffold out of it. And we wanted to navigate, or our project turned out to be in between. So it's an example. And these were like the first sketches we did. On the left side, digital sketch. On the right side, we took little branches from a beechwood tree and did that manually, and had the idea to keep the force flow along the fibers, to just flip them and connect them longitudinally so that the forces can keep on flowing. But then in architecture, because a tree is an open system, and optimized by nature to move also, we needed to close it, to form loops, so that it becomes a structural entity. And this is what you see on the left side. And this is quite complex if you do that manually, but we work with computer technology nowadays and figured out quite quickly that you can form, let's say, in that case, platonic solids out of it. For example, on the left side, that's an octahedra made out of 6 branches. And on the right side here, you see, for example, one of these here. This is 4 branches forming a tetrahedral cell. And then you can connect them, so you have a larger module, and build large structures out of it. On the bottom right, this was also an approach more iteratively growing the structure. But then you can see it's difficult to close loops. So these were different approaches. We looked at it. And with these, this is the octahedron grid. You can form these endless structures if you have an ideal branch. And the tetrahedral grid. And then we went into the forest and got some specimen. This is from several trips, and we did, like you did it probably, we're not allowed to work with a chainsaw, but we did it with hand saws. And here you see Christoph, that's our project lead. And so we collected, usually after the felling season, the parts of the tree crown that usually remain in the forest, of mainly beechwood, but also hornbeam, and brought that to school, and then started digitizing that. And at the Angewandte, we have RTEC structured light scanners, and so you get the basically one-to-one scale model right away in the computer.
So this is what you would see on this, what Daniela is seeing on the screen at this moment. So the thing is, with this sort of machine vision tool, you cannot look at what's really physically happening, but you need to look through the screen, through the machine, otherwise you can't handle this sort of motion in space and capture the geometry.
So it's basically photogrammetry in real time, but three-dimensional.
It's in real time it constructs this 3D model.
So it shoots these light lines on the object and measures the time back, and like points that are closer, and then the light's back faster, and so it reconstructs a 3D point cloud in real time.
So therefore you always have the perfect scale of the model.
Exactly, and that's the big plus in comparison to photogrammetry, that you don't need a reference, it's in perfect scale.
Yeah. And this way we were also able to later on, you will see, produce a large amount of, or a large catalog in relatively short amount of time. Because what we would usually do is we put, we put texture on the ground to have a background, and scanned the piece twice from two sides, and the two halves were stitched together in the digital model, co-aligned and then merged, and it was easiest if the background had more texture, so that it would be recognized as a plane that you could delete it later on.
Yeah, and also helps with tracking a lot.
Yeah, exactly.
So is that doing a LiDAR scan, or what is going on in the?
No, it's structured light scanning. Yeah, LiDAR I think sends out a signal, and I'm not sure which waves it is with LiDAR.
Laser.
Yeah.
This is a combination of photogrammetry and laser scanning. That's why they call it structured light, because it's light, but it's a
like an
photogrammetry.
invisible pattern that's projected onto the surface.
It's lines. Yeah.
So there would be, if it's a flat surface, it would be just straight lines, and because of the curvature of the lines, you can then compute the surface.
Yeah. So this image you see here on the screenshot, this is probably 1,000 frames. And if you look at an individual frame, you can actually see, when you look from the direction the scanner was shooting at it, you see the lines. Yeah, so it's basically just projecting a pattern.
Yeah. If you're interested, or tomorrow or the days after, I believe we also have videos of this, like capturing. Yeah. If you're interested in seeing
also
how
files,
it works.
if you want to take a look at it. I'm not sure of these ones, but I don't want
maybe just ask that we save our questions and write them down, because otherwise in the recording nobody will hear, like nobody hears me in the recording now, you can't hear me, right? So maybe just keep them and then we can hand around the microphone afterwards.
Okay. Yeah. And so after the scanning, we usually ended up with a catalog of branches. This is one from, it's actually the first and the second row, because we numbered them by the year we picked them. And then we went through a process, because with the raw data, it's basically just points in space and vertices and mesh faces. You cannot really compute that structurally, and so we had to simplify and rationalize the geometry, and that's something that has been done before, and usually it's reduced to these centerline models, because this is also what structural tools are calculating, and then every line basically gets its structural cross-section to calculate with, and this is what we have for every branch arm. We have like one cross-section that is used for structural calculations. But for all the simulations we do after that point, we usually only use the center lines as information, and the mesh is just for visualization, the geometry, and then comes back into play in the digital fabrication. But in everything in between, we try to reduce the amount of information to the minimum.
Something just to point at, it's not really. We put markings at the ends that we would also include in the scan, and in the 3D model we placed points there, and later on used them for referencing. But you'll see.
Yeah. I mean,
I just wanted to show it now, because later on I think.
Yeah.
Sorry.
I think you can see it in the robotic fabrication. Right. Yeah. And so from our idealized endless three-dimensional grids of tetrahedral cells, the reality then looks a bit different because every branch is different.
Yeah, and then the system works like this. So you have this is like a kinematic model a little bit. So we figured that given the situation of A, B, C, D types of joints of branches, we could still form the cell by shifting the branch ends along their axis, but also rotationally it can vary. So you have two levels of freedom that would allow us to compose such a cell in most cases. It sometimes doesn't work if the angles are too different from one another. It wouldn't work, but in most cases it does. And then we came up with this sort of workflow in which we first composed this infinite regular structure or framework, and then we placed the actual specimens from the set. And as you can see here, and of course none of these elements are the same, so at the connections that in here are perfect because they're all identical, here you have these sort of gaps. And then using a physics-based simulation in Kangaroo, we co-aligned all branch connections simultaneously. And here you can see a short video of that form relaxation process. And now we figured, okay, so this sort of global structure is a given form. That's of course also designed top-down. But then another design element is how you place the elements from the set in this sort of structure. So that's a sort of design by sorting in a sense. So it's more a curation process rather than a direct effect of. So you can't really control the outcome, but you can direct it towards a direction a little bit. So what you see here is 3 examples of the same structure and the same set of branches placed in a different configuration. So here we place them according to vicinity to this sort of attractor point. So I think smallest elements in the closer vicinity, the largest further away. So it has this strange sort of expansion towards the periphery. Here we assume the load case scenario using this sort of regular structure and placed parts according to utilization or cross section. So where the highest stresses were, the thickest elements would be placed. And here I think we sorted them according to angle. So the widest angles at the bottom and the narrowest at the top. And you can see you have 3 completely different designs with the same ingredients.
Yeah, and the same topology.
Yeah.
Yeah, and
keep going.
Yeah, and this can also then be used as another design approach, that you can start taking different types of wood. And these are 2 examples. So we use the hornbeam and beechwood, which grow with similar angles, have a similar angle range. You see here, this is a Gaussian or a bell curve, basically. Because when we started that, everyone told us, no, every branch angle is different. You can't construct with it. And then we did an analysis, and now we've scanned over 170 branches. And they're usually in this quite narrow angle here. You see, like most of them are between 35 and 55. So it's not of the beechwood. But then when you look at oak, for example, oak sometimes even tends to grow back down and has larger angles. And then cherry trees have usually also sometimes knots with where like 5 or 4 branches go off and not just 2. And so this can then also be used to design structures with the same topology by choosing branches from different tree species, for example. So also the idea that depending on where you build a structure and what type of wood is available, you come up with a situated design basically for that region, depending on the wood trees that grow there.
So the material used has an actual tangible spatial effect, not only texture and color as you usually would have in design, using different woods or the dimension of members, but here you have sort of geometric effect. Oh, sound.
Yeah.
It was really noisy.
Yeah. And then quite quickly we jumped also in digital fabrication tests, and the first approach or idea was also to get rid of the bark, because if you want to build architecture, this is usually the area that starts rotting very quickly. And the most accessible tool also we had at Angewandte to do that, because I'm running the workshop, is our 3-axis CNC router. And it was like, okay, we do a first test with smaller branches we can fit in there and build this frame structure we could adjust, and then just printed out the image, you see it below here, and try to fit the branch in as close as possible to how we had it in 3D, and then cut away the bark, and also here simple half-lap joints. The problem with that is, I don't think you see it here, is also when you cut with a rotating tool from just one angle, that you get the grooves and you never get a precise joint. And so we had to manually post-process it quite heavily to make it fit. So it was, I think, a successful test to approach the whole process by not using it afterwards, and like to find something that's more adequate to what we wanted to do, more fitting.
Ja, mit den Pfeil runter.
Yeah. Want to take over?
No.
No. Yeah, and so the next step was then to use the Angewandte robotics laboratory that is connected to the wood workshop there, and we have a big KUKA robot with 120 kilograms payload that's set up especially for milling. And so we looked at this approach, because with a 6-axis robot you can actually cut along the normal vectors of a surface, so you should be able to get precise cut and also grind away the bark easily. Yeah, here, like along with a rotary tool. But the problem we discovered quite quickly is, and I mentioned that before, is that nature has optimized the tree crown for flexibility because of the winds. And so tree crown wood is way more flexible because it has a different macroscopic structure also than trunk wood, that the vibrations were too high, processing it with a rotary cutting tool like that.
So at some point the eigenmode sort of vibration of the tip resulted in this sort of crash. It would at some point hit against the tool and then crush it. Yeah. And we had to stop the process.
Yeah.
Also, we were quite limited in the way it's fixated, so that's another story.
Yeah.
Interesting, it doesn't start.
Yeah.
Yeah, so we continued with, focusing on the structural, as you see the flexing, yeah. But that's also due to this, like, thick drill, and he didn't bother to change the, dimensions, so went in straight with. And then so we skipped the whole, bark removal process and only focused on the joint integration, like a very minimalistic sort of approach, because we were saying, okay, what we are aiming for is in the end a structural sort of scale, and we left the sort of product or the object area a little bit. And the first, and also from learning from the sort of routing or milling problems, we figured, is it possible to come up with a joint that can be produced by cutting instead of routing? And we came up with this scarf joint that exists also in traditional. This is a specific joint, but we also realized that it's not a good idea for these types of structures that we are using, since we are not having parallel assembly vectors. So when assembling V-shaped elements, we would have to bend them and then snap them in somehow, so use the material flexibility to actually assemble it. Also, you're quite limited in the sort of length of the overlap, because very quickly these sort of points become very narrow and fragile. So at the end, it's pretty, but it's not very effective or structurally feasible. Okay, I think we can move on. Want to continue? And then we developed, we re-evaluated the joint, and we came up with a modified lap joint. And the idea was to use conical steps to find a form that would allow position fixing of the two elements. So due to the conical shape, there's only one position these two elements can be fixed, as opposed to a normal half-lap joint where you have some freedom to slide it around in order to find a position. Here you have only geometrically one defined position. Yeah. And then here we did some tests. Okay, what's the scale of it? How can it be produced, and so on. Here, these are some simulations of the robotic, tool paths with a circular blade, because obviously the circular blade is the most precise. But at the time we were preparing for this exhibition, and the space in which we wanted to put it has a rather low ceiling, or
for our purposes.
So it's got a limited height dimension, and we realized, okay, if we want to produce a structure, we need a certain amount of these sort of modules in order to have a complete structural cell, and therefore we had to compress the entire thing so that in the end the branch elements themselves became really short, even though they were much longer. So I think if we were to use only the ends or overlaps at the ends, so the maximum length, I think we could have produced double the height, easy. So, and because we had to compress it, we realized that robotic cutting with the circular saw is impossible, because we would hit the other side, when cutting around the node or the bifurcation point. So we had to change the tool, and we used you can maybe see it here, a chainsaw hooked to the robot, which was a quite rough
electrical one.
Electrical one still, but yeah, it was pretty rough. And then and also modify the So here you see what we did, and you can see later on we we can show this. So this is the how it turned out. It's quite rough. Yeah, it's more or less the geometry, but So and this is also you see how the choreography of cutting happened. So first there's this sort of array of parallel slices in one direction, and then it switches over to the other direction.
Also have to say we collaborated with Philipp Frey, who runs the Angewandte Robotics Laboratory, and he was a major contributor to that project and did all of the robotic work.
Yes, and also together with him we developed this mounting tool, like this device that's a whole project in itself, like how to fix these things on the rotating table, and he was also the designer of that to a large extent. That's him.
To minimize also the vibrations. So we added these cantilevering arms below them.
Yeah, and the
so he did a lot of work.
And right. And then that's the production. That's the production for the exhibition, where you can see that we assembled modules, and because we realized, okay, we have this sort of rough tolerance from the chainsaw, we glued them together, even though that wasn't obviously our initial intention. We said, okay, so it's like we have another week before exhibition opening, screw that, we need to make it happen. So we glued them together, and then those we glued it. But even with what did we use?
Normal wood glue.
Normal wood glue. Okay. But and also that's another story. At the time when we were bringing the wood to Philip's workshop at the robot, that was a time of what was it, 3 months or so minimum. From that moment we collected it in the wood?
We collected the wood in February, March, and the exhibition was in September, October.
Okay.
And we scanned them.
We scanned them when they were fresh, and then we wanted to produce them when they were dry, and they were a different shape. They didn't only compress in dimension like you would expect from wood, but the geometry changed. Yeah. But we were lucky that we had to compress the structure, right? So the geometry difference closer to the node wasn't that high, but still the precision was quite off. Yeah,
and then also the joints were simply in space, in the right position. Mm-hmm. It's just not exactly on the branch as it was in the 3D. It was just a little bit offset. Mm-hmm. So in the end, the whole structure fitted together perfectly.
Yeah, right. It
easily.
Was just happening slightly at a different.
Yeah. So if you have enough flesh on the branch, it didn't matter.
Yeah. Also, we realized, but this is more of a problem that you don't have, luckily, because we put it in the basement. We don't have. At the Angewandte, many things are really like. We have to improvise a lot. So we put them in the basement, and I think it was too humid, or they picked up this sort of fungus in the forest already. So some of the elements weren't really stable anymore.
Yeah, they became quite brittle. But I think that's from the forest, because we usually pick them after harvesting, so they were lying there 1 week or 2.
Yeah, so for an installation like this, it would work, but actually this wasn't really structural anymore.
Yeah, so that was the first prototype, and then Corona hit and we had a short or a longer break in between, but after that we had the opportunity to collaborate with 2 performance artists that wanted a stage made out of these branches to interact with, and so we had the opportunity to build a second prototype 2 years later and start with everything we learned already
and do it and just scale it up a little bit, right? Use larger elements. So it's this comparison.
And you see here like a tetrahedral cell is quite compact, and here it's still very large and the overlap is somewhere here. And it also has a different typological structure behind it. It's a bit more open. And for that, because we increased the size, we could use the circular saw blade again. and because we had enough distance to the actual knot, and so we were able to cut the same joints with a circular saw blade with a much higher precision. And that's exactly the same geometry, so they fit together, but then cut with a saw blade.
But here there is again a deviation from this sort of very precise moment, because there we had to use the fresh wood. We would use fresh scans, but also fresh wood for the construction, and then left it outside for a while, and it was already cut into shape and then continued to dry. And you can see slight warps in the sort of otherwise straight planes.
Yeah, so it dried being assembled, and so the branches cracked like from the center out. Yeah. And so a lot of and these we screwed because initially it was planned that the stage basically moves. They wanted to have these performances at different locations, so we had screw connections, you see here, with 2 bolts. And they basically and we had it, because they didn't move it, we had the opportunity to see how it behaves, and it was standing from March till October, I think, for a whole half year. Study term. Basically.
In the beginning it matched quite nicely, and then after a few weeks or months, gaps increased, of course, in between. So if it was dried properly, and it theoretically would be possible, but yeah. So this is the collection of different joints we tested. Here, one that we still are showing, right? Yeah, that one. That's a completely different approach. Do you wanna?
No.
Sorry. Here we asked ourselves, okay, so here using a robot is a pretty high-end and not very accessible production method. Can't we use digital tools for a primitive workflow as well? So the premise was, can we assemble a structure using these parts with only a hand saw, some fixation, and a mobile phone and a pen, using AR. And on the top left you see the test we did with tracing lines along where the joints should be cut. And then there you see the sort of tray. At the end of the video, I think it's briefly visible how it looked. It's obviously not very precise, and we had some tolerances, but with a more simple joint it would still be possible to assemble a structure. Unfortunately it remained with that test only, but this is something we want to bring along, or we are currently looking into for the next project we are doing, which we're not talking about today, but at the time this was the only test we did. And then what else? All right, this is the neat sort of robotic fabrication we did for the final installation. And you can see the fresh wood, right? It's quite juicy still.
You could sometimes really see water dripping after cutting. It's quite helped with not being too dusty, actually. But
and then that was the final, or the comparison of the two.
Basically at the end of the official research project phase for the branch formations, the two structures we've built.
Yeah, and then this is another slide we just added to show you how we sort of think about design in this context, that we came up with a structural logic or principle and a design based on the logic of the material, and then in a sort of aftermath or speculative inquiry, think about possible use case scenarios. So it's not exactly designed for a use or a specific form, but it's really, here we looked at, okay, what can we do, how could these sort of structures become architectural applications. And they also remained quite abstract, but it indicated ways of how it could be continued or brought into practice. Our project remained in the sort of abstract space, but it was important to us to show this case of the possibility of the transfer into another realm. Yeah. Here also, once again, this sort of structural evaluation of a regular grid, showing the different distributions of different cross-sections. So the cross-section optimization that happens here, that could be aligned with the availability in a set. Which again, of course, would also produce a deformed formation, which theoretically would also need to make necessary a feedback loop, because then with a deformed form, you would need to re-evaluate the structure, reposition the elements. So we ran through that process a little bit, I think, for one publication, but also not quite completely in depth. So, but yeah, there's new fields that could theoretically open up, which we didn't follow, but yeah.
But then also when it comes to architecture, it's a scale jump, also when it comes to the tree. And we also had these ideas that you don't need to work kind of with the material that's there. This is one approach we took, but you could also see the forest as a living organism and not cutting down the trees, but like just harvesting the parts of a tree you need without cutting it down completely, more like harvesting fruit that grows somewhere, and kind of this approach to like other living organisms. Yeah. And this is then again related to the inventory. Like the larger your catalog is, the more or the closer you can build to the digital ideal. So this is then the mediation between kind of the organic material and the top-down design you want, and you can navigate that field freely.
Theoretically.
Yeah, and all of that is basically summarized in the book we published, parallel basically to the last prototype. And it's focusing on the workflows, not really on the end result, but basically what we've shown here, kind of a more how-to.
Yeah.
And there's also contributions of collaborators that write a bit about kind of these basic questions, like the areas we base our research on, craftsmanship and the biological structure of wood. But then also we asked a couple of colleagues to philosophize a bit about the aesthetics, but also kind of the kind of where this could be pushed, like the future of this approach, kind of this the follow the material approach by Hélène Frichot.
Yeah, and now, so that was when the project was finished, but then we got invited this year. Was it this year?
No, last year in November, I think.
Yeah, to do another structure in an exhibition in Munich. It's called Trees, Time, Architecture. And it's gonna open on March 13. It runs through September 14 next year in the Pinakothek der Moderne, Architekturmuseum der TU Munich, Technical University Munich. And it's organized by Ferdinand Ludwig and his team at the Baubotanik Institute, the Living Bridge and these sort of things. So they are interested in this mainly, but they invited us to also contribute because they are spanning a large spectrum of approaches, from ecosystems all the way through building and
towards architecture.
And somewhere in between is our work, and this is what we designed. It's also related to the previous structures, slightly modified again. And at the moment, do we have another slide? yeah. This is the design, and this is the
fabrication plan.
The fabrication data. So all the vectors and planes for the joints. So this is used to create the toolpath, and and also we did some tests with how to join these elements, avoiding screws and glue. And we came up with the idea of using PET bottles and their capacity to shrink when heated, because they are, they're blown into form based on tiny forms. What's it called?
Yeah, they are injection molded.
Injection molded, and then blow vacuum. No, what's it called?
Extrude.
Blow molding.
No, blow molding
process.
Yeah.
And so when you heat this form, it contracts back into its original state. But also PET, I think, tends to shrink when heated in general. And it applies quite a lot of pressure when it does that, because it's a strong material, so it doesn't really break. And it contracts these things together. And our idea is to use it instead of gluing, as in the first installation, for producing modules. And then in between modules, we still need a more easily reversible joint. So we still have screws. And now this time around we have two different types. So within the modules we have this sort of conical zigzag joint with the PET shrink wrap. And then in between modules we have this lap joint, which has also a slightly conical end so that it would fit into place. And it's going to be bolted like that, so that an assembly team at the museum, without us being there necessarily, can do it. So we were like, we can't ask them to do this sort of experimental heat gun PET thing. So we need to provide them with something easy to do. And also possibly this thing is going to move to another place after the exhibition. So design for disassembly played a role here too.
So we can assemble the tetrahedral cells, and then in worst case we just cut the PET bottle open and disconnect them again, and the PET goes to its intended recycling flow. But for us that's more the permanent connection, and we just ship the modules. Yeah. And then it's just adding them. One thing though is that we adjusted the zigzag pattern, because we were afraid with the PET bottles, as you can see, sometimes they're not perfectly fit, so that we have a smoother transition, like less height, but keep the same contact area. So we have the same amount of friction. And so, because it's a digital fabrication workflow, we could simply adjust the zigzag pattern again. And also it's not weakening the cross section as much, so it's closer to the flush cut. And these were the reasons to adjust that as well. Yeah, and that is currently in production. Like, we're hoping that Philip started yesterday. He hasn't. We had some struggles, which comes when you use this high-end technology. There are always errors, and the more complex the technology becomes, the more prone it is to errors and the more difficult to find them. And so we're still in the process of cutting it.
We are planning to set it up in the beginning of December.
Yeah, hopefully.
Test build up.
Yeah. Because once it runs, it's 72 branches now, so it's also quite larger. The first one had 68. Second one 36, and now we're like 70 something. But theoretically, complete cutting time would be 9 days if the system runs. So it's actually not that long. So it's usually like...
Yeah, but also we have a quite streamlined work process by now. We are using, every time we are doing this, and this is now a time span of a few years, we are using the same files, we are using the same device to mount it. And it paid off by now that we really had this sort of workflow. And some of these tools that we developed, we brought for the workshop tomorrow. So you get to use them too. I mean, the digital ones, not the robot. obviously.
Once?
We didn't bring a robot.
I want my money back.
Sorry.
You know, but still in production, it's very custom, so it's not industrialized. So also this time we had to do a lot of adjustments, and then especially Philip, he needs to make sure in the three-dimensional structure that the joints are in a good position to transfer the flows, the structural flows, the forces, but they also need to be then laid down on the fixation device, and he needs to be able to cut them. So he cannot simply rotate them freely in 3D space. So this is still a lot of manual work a person has to do to actually go through the whole file and make sure they're in a position that's also...
Especially in the case of Philip's workspace, because this gigantic robot is positioned in a quite tiny cell. So it has a quite limited. It could theoretically do amazing things, but it's so limited in its reach. So it's literally doing this, and it's not really moving. And that's another So when you ever, I think this is really quite a limitation, and it causes quite a lot of problems because it's
Yeah. I mean, he has a 7th axis at a rotational table.
That helps, but yeah.
But this is also kind of this more arts-based approach. We develop a workflow that works to a certain extent, but it's not our interest to make money with it and put it into production. And we can improvise and develop these workflows in that environment. And we're lucky and privileged to have access to it.
Yeah, I think that's it. Right?
Yep.
Yeah.
Thank you so much for a super generous and insightful talk. Takeaways. The book. We have the book. Oh, this is an.
Yeah. Just to add, the book is also. There's a digital version of it, and that's open access, so you can simply.
And we have it in
it.
our shared Nextcloud folder, so everyone has access to it. We also have the print version in the office, so come and get it. We will also hopefully come to the exhibition because we have a excursion budget. So in the next term break, we'll probably join you in Munich. Another takeaway is plan our robot cell large enough because we're currently applying for one.
Or fit the cell with the robot size.
Exactly. Yeah. But it's so much fun seeing the two speak together and getting very nerdy and correcting each other and getting very excited. And it's a unique way of seeing a lecture where you're open about failure and having it in such a kind of conversational way, because that's often I find lost in when we speak about digital fabrication. We often talk about what goes right. Then we talk about it as a streamlined kind of process, and I find it super, generous and open of you to speak in that way. And also at the same time, I think it's fantastic. It's perfect timing to let you loose on the students and on us tomorrow, because in a way I think we're building on the research and at the same time, we're trying not to be, and I'm not valuing this, but trying not to be as purist as you are, because this is incredibly purist. You can't change anything about the tree. We need to use the tree or the branch in exactly the way that we found it. And so in the workflows that we're trying to develop, we're also trying to make fit what doesn't fit in a way, which your system doesn't allow. But through this kind of purist, kind of obsessive approach, I think there's so much for us to learn from you, and we hope that we can hopefully through the project give you something back on the longer term as well. But I want to really open the floor for more questions, because I'm sure there will be plenty of questions. Of course, Berke has a question.
Hi, first of all, thank you for the great presentation. I was wondering more about how you dealt with the issues that came up when you actually had to build the thing. I myself also studied architecture and had the pleasure of doing a semester of design with Thomas Pierce, and it was all fun and games until I had to actually build the thing that I designed, which is something you never do in architecture. You just 3D print a little scale model and then that's it. And so once you figured out the different types of linkages you have, whether it be that sod system or what we're seeing here right now, I would like to hear more about the process on how you sort of realign this whole system back to reality. So doing a 3D scan is kind of simple. Making meshes align with each other is kind of simple. There's a lot of complex technology you can program to help you with, but when you actually have to align the branch with the robot, there's, I feel like, nothing to help you. So I'd like to hear more about that. Or did you just give that to the person who was dealing with the robot anyway?
Yeah, I mean, in general, I think it should have been visible, is that we have this step-by-step approach. Like we try in little steps and then learn from them and adjust the way. And I guess you're specifically interested in the workflow, like digital to physical.
Yeah.
Yeah. So like the realignment. I mean, Lukas, you tried to touch it. We didn't say it, but we had. I mean, that comes from, let's say, our education as well, how we studied architecture, that there are some basic principles already in place. And so while scanning, we already thought about kind of how we process it later. And so before we started, we knew we needed some markers or references. And this is why we drew these crosses on the branches before we scanned them. And we had, at each end, we had one. So 3, and this is usually enough. You need 3 points to place an object in place, not more. And these were also the points Philip used on the robotic fabrication. So it didn't matter how he put it in place. Like we had the fixation device with the little arms to adjust, put the branch, and then he was just measuring in the 3 points, and then with this data aligned the 3D file to the actual physical object, and then cut it in place. And this is why we stepped towards robotic fabrication, because on the 3-axis CNC router, that was like just as close as you can like eyeball it. Yeah? So we also simulated actually the branch in a physical simulation software with Kangaroo as a solid object and let it drop to see how it lies, basically flat, all the 4 branches, to be able then to screw them. But with this frame, when you manually try to hit, you always adjust it a little bit. And like we did the first test, learned from it, we're like, we can never reach the precision we need to find something else. And so kind of this step.
Leave alone standard.
Leave alone standard, carpentry tools like table saw and so on. These are made for standardized elements, and here we have these weird artifacts, and the robotic arm is a pretty good tool to do this. It just comes with quite an effort in programming and so on. But yeah.
And one aspect why we added the additional points, like we had usually 3, 4 more on each side of the branch, was that we were already afraid if something goes wrong in the fabrication, and we need to like readjust, and Philip cut away a part already, we cannot measure it in. So we had these backup points, but these usually not drawn because there was no automated process of getting the points. So this was done manually by us, looking at the texture and placing the points, basically. Yeah?
I have a question about the joint. Because each of the unit each of the Y is different, the scale may be also different. So how to define the joint scale? For example, for the very big one, big Y, so the joint may be bigger, or it's just depends on the radius of the wood. So I have this question. Thank you.
Okay. No. So actually, the joint is exactly the same on all of them. So if you take two, like this one and the other one, so that's from the second time we cut it from the first time, they fit together, even though these branches were never meant to fit together. So it's one singular joint, and if you basically increase the diameter, it's just that these cuts become longer. But the pattern is exactly the same. So theoretically, you can match every branch with every other end. Sometimes, if they were super tiny and not perfectly aligned, Philip had to adjust the geometry a bit, so there are some custom connections in some areas. But overall, no matter if the branch has a 30 centimeter diameter or 5, they would find a position where they match. So it's just the geometry is the same. Yeah. Yeah, we don't have a detail, but
no, we don't have a detail.
Yeah, but that's a cutting pattern. So it's kind of this fan, basically, the conical fan, and that's just placed everywhere in the angle we needed. And so theoretically, you could take a branch from up here and connect it with one down here, so they would match in geometry. Yeah. Okay.
Thank you. I have another question regarding the abstraction process, like from scanning to a centerline model. How automated or manual was it still? Because we are also developing this as a pipeline and trying to make it have it run on a server overnight. What are your experience? How did you solve it? Did you have to do it manual, or did you find a definition that does it for all cases?
Like not one for all cases, because it's usually how it's done. It's that you have slices through the mesh along, like on a branch, usually like orthogonal to the length of the branch where it branches off. And then sometimes, depending on where you hit the node, you get like a weird cutting outline, or sometimes there are little twigs still going away. And so I would say from like the 170 plus branches, 75% are usually working with the standard parameters you set at the beginning. And then you can batch it, automate it. So we had a Grasshopper definition that was just loading in the OBJ files and doing that. And we ended up with a file with all branches in there. And then we manually went through and looked at the ones that were falsely oriented or that had like a weird polyline that didn't work to connect it. But it's very, also we sent a definition, I think 2 weeks ago. This is very specific to the branch geometry, but also in the current project we are looking on a way of more smartly generating skeletons in general, but it's very difficult because you always start with mesh geometry that has like just points and faces and no other information to work with. Yeah, but I would say 75% is automated and the rest is manual override, switching a bit.
Yeah. I want to add that to address this question on a general conceptual level, I think the point is always, or the question is always, the scale of the production. So to which extent is a full automation really necessary or useful or feasible, however you want to call it? And to which extent is a DIY half manual, but therefore more robust approach more applicable or more productive? And in our case, we realized, okay, we realized we could maybe get to the point where it's fully automized, but it would consume so much energy and take time in our project that we can use otherwise, so we didn't do it. So I think I also know this sort of ambition to script things down to the magic button that produces a design and builds it at once, pretty much, based on an intelligent parametric system. But the reality is that these things are so heavy often, and and very complicated if they even, and they don't allow the sort of flexibility of adjustments, leave alone intuition. So yes, I think these things could be possible if we are talking about industrial production in large numbers, large scale. But for something like this, and probably also for something that you are doing, maybe as an advice, don't try to push too hard in this direction.
Okay, thank you.
Yeah. No, very good point. Yeah, but then it also has to do with your own personal skill level and where you want to invest your time. Like if you want to learn, for example, Grasshopper that way, go for it. Script it down to the thing. Because in our case, we set it up once and it doesn't take us that much time because we've started working with explicit history before it was named Grasshopper. So we grew along it. So it's easy for us to just plug stuff together that works basically and then adjust over time. And so instead of sitting 2 days for the 86 new branches, it took us 2 hours, And then it's worth if you're only sitting an hour to set up the script. Yeah. So it's always also this mediating of time and skills and tools you have available.
And also maybe a question of where do you want to go? Do you want to go towards optimization and refinement of processes? Are you interested in processes and data management? Or are you interested more in the freedom of design and exploration, which also comes with its own risks and challenges? So really, this is maybe also something that is part of the answer to this question. So yeah.
I think Aaron is definitely in the camp of he could, in your camp of being in explicit history before Grasshopper kind of that moment. But I think still this advice of, parametricize to a certain point where it makes sense and where it doesn't overtake intuition and where it solves 75%. And when sometimes you need to spend 2 really boring hours of listening to a podcast and drawing center lines by hand, that's fine. And it's it's sometimes a bit of repetitive stupidity also to better understand systems before completely automizing them, because what we're doing in these projects, the proofs of concept, right? And you could then give it to a programmer and he could spend or she could spend a year on it and make it completely watertight. And what we're doing in study projects is proving workflows, testing workflows, developing them, creating visions, for something new, I guess. Question?
Many thanks to this. It's very inspiring and very interesting, I have to say. And as Aaron maybe wants to know, the second design you created for the theater, for the performance, how much did the parametric thing you created was it 50 by 50, or was it you did it hand by hand? Because it's more like an aesthetic thing, I think, because it was just for a stage, right? It was more like okay, what do we need here? Where do we want to dance through? Or where do the actors need to, or was it made by Grasshopper as well? Who made the decision?
That's a good question. And it came at a time after we had developed all these systems and went into how could this structural optimization. I think that was the moment where we were most obsessed with the parametric system, like how to optimize the positioning of elements from a set according to structural necessity, let's say, or utilization. And how then every time you find a configuration of elements, it changes the form. And to run, a feedback of, this back and forth in between the two. So that happened, and we came to a point where we were like, okay, we could be doing this forever, and but we never got really in depth to it. But then at the moment where this project came along, this moment had passed already more than half a year, I think, or a year even. And we realized, okay, so it was more of a revisiting of what we had done before. And we realized, okay, now we need to do it again, and we need to do it quickly. And there's no way we open up these gigantic definitions and scripts we have, leave alone that we didn't know how to handle them anymore. It was like, I don't know. And so we took this chance, or this opportunity, let's put it that way, to modify the system into something more robust. So at the time we were more interested in this sort of robustness and accessibility, or let's say low threshold approach, that we extracted the sort of key moments from the scripts and composed a definition that would allow us to manually place these elements, and the automation happened on the sort of form finding end. And by the way, that script that we developed then is the one that we are bringing tomorrow. So this is what allowed us to now go out, or to make it available to others to be used, because it doesn't require in-depth knowledge of what's really going on. And what I wanted, but it was really a pragmatic decision. So we designed the overall structure, or the overall, say, regular form, this one what you see here in the axis model, to give a rough configuration of, okay, this is width, height, and so on, and dimension of it. And then we positioned the elements inside that framework, roughly, I believe, at the time, using the thickest or the heaviest elements at the bottom and the thinnest at the top. So that was the principle, and we realized, okay, we have what was it, 30 something, 40 branches. We could do it manually. We sorted the set. We took the largest ones, put them at the bottom, and so on. So we built it all the way up, and then every time, you will see it tomorrow, every time you position them, you will see the model change. And once we saw it doesn't align nicely, we changed one branch here and there, until after a work of 2 days listening to podcasts and so on, we arrived at a model that we thought still fits this sort of basic idea of big elements at the bottom, smaller ones at the top, with a configuration that we thought was working in the space. So there, yes, we sort of had this dialogue with the materials and the exact form in the space and so on, but in a quite analog intuitive process, let's say.
Yeah, but also like taking back a bit more agency as a designer. Like, we have set up a strict typology, we have the material that defines a lot of the final outcome, but then also we don't leave it like just to the system we've set up and the rules, but we also step back in as the designers and make certain decisions.
Yeah. Same here.
Ourselves.
This is the same.
Yeah. Yeah, and this used exactly the same process. So we set up the typology, and then literally manually placed the branches and changed them in position until we got like a structure. We had the feeling structurally works, it doesn't fall over, and fit it in the space.
And nerdy detail. Here, again, we did a slight change to how we did it before. Because before we composed the structure all at once. So every branch individually placed and exchanged. And here, we had the idea to pre-assemble modules in digital space, because by now we realize, okay, there's certain rules in how angles fit best together. So in the tetrahedral cell. So you have two pairs of Y-shaped elements opposing one another, right? And you want to make sure that both of them have more or less similar angles. So you can use two wide ones and two narrow ones, positioning them opposite of one another, and then you usually arrive at a nicely aligned cell. So that plus this sort of thickness matching roughly, and then from the modules we compose the model.
Yeah, but that was also due to the specific decision that we wanted the pattern be visible in the final structure, because we thought this is a completely different audience to what we are working with normally, because it's in a public museum and 90% at least are not going to be from an architectural or design background that go to the Pinakothek. And we wanted not a super crazy structure, because we can go very crazy with that system. Because if we match 4 different tetrahedral cells, you can still build the whole structure out of tetrahedral cells, but no one will recognize. And can you show the last prototype? No, the one before. Yeah. Do we have the overall picture somewhere? No, we don't. Okay.
This comparison.
Yeah. Yeah. And so here we had kind of, you also see it, that it's very regular. But then we decided here in the front that we give it this leg, basically. But depending on the angle you looked at it, you weren't aware that there are repetitive cells in it. And specifically for the exhibition in Munich, this is also why it's much larger, that you see a larger cutout of this repetitive pattern, so that we can show that with a very irregular building element, we can build very regular structures for our definition.
A systematic organization. And I think you would see it best at the top image there. It has this repetition of the organizational principle.
Yeah. And this is why we pre-assembled the tetrahedral cells and then placed them in space, because then we could control the overall shape much more.
I think we just have time for a very, very, very short last question, which maybe needs to be a yes/no question. No.
We're also here 2 more days.
We can answer questions for 2 months.
Continue picking the brains for the next 2 days, which I think we'll do plenty of. I'm also just aware that we're taking you out for a meal, and a reservation is soon, and it's not because you're boring us, but it's basically now, which is why I'm getting nervous. But also, it's such a great sign. No, sorry, we're not taking you. I mean, we can continue this conversation over the next days. But is there maybe one final super important question, burning question?
Where do you go for dinner?
I don't know.
Okay, maybe. Thank you very much.